Okay, we will discuss here the various types of artifacts or the noises which corrupt the biomedical signals, and then the potential solutions to reduce or remove that interference from the signal. Okay, so what are the various uh, types of interference which are added to the biomedical signals during data acquisition, and then what are the techniques available with us which are used to cancel that interference from that signal, that we will discuss basically. Okay, and the cancellation of artifacts or interference is very important as far as the biomedical signals are concerned. Okay, so if you have a ECG signal, so it gives information about the electrical activity of heart. Okay, similarly you may have a EEG signal which shows the electrical activity of your brain. Okay, so you may have PCG signal, phonocardiogram, which is nothing but the heart sounds. Okay, because heart is a mechanical pump, so when it vibrates, it produces certain sounds which are basically recorded using some pressure sensors. Okay, so the stethoscope that is used by the cardiologists or doctors, that is basically nothing but used to listen to the heart sounds. Okay, which is basically a PCG signal. So all these signals they carry some useful information with them. Okay, so any part which is irrelevant or which is embedded to this and which is apart from this important or useful information, that is interference for us or noise. So there are different types of noises, or in fact different sources of noises. So we classify the noises into different categories. One may be a random noise, and you may have a structured noise, and then you can have a physiological interference. Okay, so these are the different classifications of the noises which may corrupt this information bearing signal. Okay, so the purpose of this signal processing is to make this signal clean or noise free, so that all the features that you extract from the signal after processing it, they are accurate. Okay, your diagnostic decision must be accurate. So that will be accurate only if the signal itself is clean. Okay. So what is random noise? See, if you have a some, suppose you have patient which is, and there is some ECG signal you are recording by placing some electrodes on the chest and on the limbs. Okay, so you have some, suppose lead one. So what are the various types of artifacts that can corrupt this information being signal? Since the magnitude or the amplitude of these biomedical signals is very less, it is in the range of millivolts or microvolts sometimes. So we need large gain amplifiers to amplify these signals. Okay. So due to the large gain of these amplifiers, the thermal noise in the amplifiers, that sometimes also gets amplified. Okay. Similarly, other sources of interference are due to your EM waves. Okay. So in the recording room or in where you have a recording setup, so you may have other electronics instruments which radiate EM waves, so that those EM waves may be captured by your cables. Okay, like power line interference, power line frequency of 50 Hz or 60 Hz, it may get it added to this information bearing signal. Okay, so that component, this EM waves all these power line frequencies, they can be eliminated by proper shielding of these cables. Okay, and proper grounding or earthing of these cables, you can eliminate that noise. Okay, and similarly, when you acquire some data from a patient, so if he coughs, okay, due to coughing, the muscle noise, which is EMG noise, it may get corrected with the ECG noise. Okay, so you are acquiring ECG from the patient, but if the patient coughs, so due to the muscle contraction, another component EMG that comes into picture and it gets added to this ECG. So you have ECG plus EMG mixture. Okay, so your objective is to eliminate now this EMG component from this ECG signal. Okay, similarly, when during data recording, if the patient moves or due to sometimes respiration also, due to the respiration activity or due to the movement of limbs or chest leads. Okay, so there is a low frequency noise which gets added to this signal, which we call as the baseline monitor. So baseline monitor is basically low frequency noise. So if you record a ECG signal and if the patient moves, okay, or due to the loose contact of these electrodes that you place on this body surface, so you, in place of getting a signal like this, you get a signal like this. So it may go up and down. Okay, so you have a low frequency noise which has changed the baseline of the signal basically. It's a very low frequency noise. Okay, so this low frequency noise is called as the baseline monitor. So can you, if you see the frequency range, it is generally below 1 hertz frequency. Okay, so it means you have to use some kind of, if you want to eliminate this type of noise, you have to use a high pass filter. Okay, so it will pass only the high frequencies. This low frequencies will be attenuated or it will be stopped by this filter. Okay. Similarly, you have in the high frequency noise, there are two major noise. One is EMG and one is your power line frequency or power line interference. So power line interference is generally occurs at 50 hertz or 60 hertz, and sometimes you have this harmonics also. It means if there is a frequency of 50 hertz, there may be a frequency of 100 hertz. Sorry, 150 hertz, 200 hertz, and so on. Okay, so you must have a filter for elimination of that. You can use simply a notch filter to remove 50 hertz component, or if it is a there are harmonics also, you can use a comb filter. So notch filter will have a response like this, 50 hertz. If it is a comb filter, it means you are also eliminating its harmonics, not only this 50 hertz, but its harmonics. So 50 hertz, then 100 hertz, then 150 hertz, 200 hertz, and so. So at all these frequencies, you have a null point. Okay. So these frequencies are stopped. You must have a filter like this, which we call as comb filter. Okay. So different. So this is what is basically called as a structured noise. Okay, structured noise, or you can say, because see, it is a particular frequency. You have only one frequency. So okay. Anyhow, we may not have information about the phase, so the phase of this may shift. Okay, but the frequency we consider that it is remains at 50 hertz, or even sometimes it may be less than 50 hertz, maybe 49 hertz. It may go up to 48 hertz or 51 hertz. Okay, it is not always 50 hertz. Okay, so in that case, in such a scenarios where if the frequency of the signal or this noise in fact is changing, So you cannot have a fixed filter which will always remove this 50 hertz component. Okay, if the frequency of this noise becomes 49 hertz, it means you have to design a new filter to eliminate this component. Okay, so then we have some filters which have self-tracking capability. Okay, that even if the frequency of the noise in the signal changes, it will change its response, or it will adapt its response according to the noise frequency. So that if the frequency, it means it will have a moving frequency response basically. Its null point can go from 50 to 49 hertz, or it can go from 50 to 51 hertz depending upon the frequency in the signal, frequency of the noise in the signal, which we call as adaptive filters. Okay, and then so these are two major sources of noise: the power line frequency and this baseline wander. So one is low frequency, one is a high frequency noise. Okay, so there are different filters. And then another type of interference that you have is in the biomedical signals, which is more important. It is physiological interference. Okay, physiological interference is a good example of this is a fetal ECG mixed with your, I can say, mother ECG. Okay, so when you acquire this data from the abdomen of this mother, so you get a mixture of both fetal ECG as well as maternal ECG. So now in this case, if you want to extract the fetal ECG, it means your maternal ECG is no noise for me. Okay, and you will see that there is a overlap between these two signals, fetal ECG and the maternal ECG, in time as well as in the frequency domain. Okay, so fetal ECG, the heart rate for this is generally high, so you will get more beats. Okay, let us suppose this is a fetal ECG signal. Okay. And correspondingly you have maternal ECG. So you cannot directly now see if the signal that you acquired from this, it is basically a mixture of this. Okay, so but when you take only when we take the signal from the chest with chest leads, we get this is we call as abdominal ECG, AECG. Okay, and this is MECG. So you can say that okay, you can subtract this MECG because it gives only the ECG of the mother, whereas the signals which you acquire from the abdomen, they have the ECG of mother as well as the fetus. So you can subtract this from this to get this fetal ECG signal. Okay, but that is not the case generally. Okay, because there is a overlap in time. It means the QRS complex or the R peaks of this fetal ECG and the R peaks of this mother ECG, they somehow sometimes they overlap. Okay, so if you subtract them, you will lose the entire information. And even if you use some filtering to remove this, you can have, you will see in the frequency domain, if you see the spectrum, they occupy the same spectrum almost. Okay, so fetal ECG and the mother ECG in the frequency domain, their spectrums they can overlap. So you cannot have a filter, you cannot design a filter which is simply remove one component from this while retaining the another component. Okay, so again for this such type of noises where the signal and the noise spectrum they overlap, you cannot use normal filters, low pass high pass filters. Okay, so we use some more sophisticated advanced signal processing techniques to remove such type of noises, and one such noise is method is your adaptive filtering. Okay, so random noise, so most of this noises that you get in this biomedical signals, they are random in nature. Okay, like a EEG is a random signal, a PCG is a random signal, EMG you can say it is a random signal. Okay, if you say about the ECG signal, ECG signal is not a periodic, but you can say it is a cycloperiodic, quasi-periodic. Okay, because every heartbeat is not same. Okay, there is somehow difference between the two heartbeats, so it is not exactly periodic, but it is quasi-periodic. Okay, now as far as the random uh, noise is concerned, so we sometimes say, okay, if ECG is mixed with EMG, so the noise that I'm now trying to remove from this is EMG, which is basically random noise. Okay, if ECG gets corrupted with 50 Hz noise, so the noise that I'm trying to remove from the signal is now a structured noise, a periodic interference, in fact. Okay, or if your fetal ECG is corrupted with your maternal ECG, so the noise that I am trying to eliminate is now MECG. Okay, it means depending upon the type of noise source that you have to use the different types of filters. Okay, so we generally classify these filters into three categories. One, we use the time domain filters, then you have frequency domain, and then you use minor filters, and then adaptive filters. Okay, so in the time domain filters, we basically process the signal in time domain. Okay, so you have some time domain operation that is applied on the signal using some filter coefficients. Okay, without basically calculating its frequency response. Although we calculate the frequency response at a later stage just to see that how it behaves in the frequency, but the operation is applied in time only. Okay, so synchronized averaging, your moving average filters, they fall under this category basically, time domain filters. Okay, in the frequency domain filters, we store directly from the frequency response. Okay, your Butterworth filters, your Chebyshev filters, so they fall in this category, frequency domain. Okay, and then these two filters, linear filters and adaptive filters, they are, we also called linear filter as optimum filters because they operate in a optimum or in a mean square sense. Anyhow, I cannot go into detail into this because you need is knowledge of the random process to understand these types of operations. But still, we will give a general uh, overview how it works basically. What is difference between the vinyl filter and your normal filters? In the normal filters, you apply some input to a system, or we call it as a filter, and you get some output. Okay, so it is a one-way process. So this filter, it may be time domain, some time domain operation, or it may be designed specifically in the frequency domain. Okay, so it may be FIR filter, it may be IR filter, whatever it is. So it has some frequency response, and based on that frequency response, the frequencies in the signals, they are passed or stopped depending on how you have designed this filter. This is what the normal filter does, low pass or high pass filter. Okay, what the minor filter basically does, in the minor filter we need two signals to operate. One is you give a input signal to a filter, and this filter, now using the equation of operation of convolution, it generates some output yn, and then we have a another signal here which we call as the reference signal. Okay, and these two are subtracted together to get an error signal which we call as an, which is your dn minus yn, reference signal minus output of this filter. And the purpose of the Warner filter is to Design the filter coefficients in such a way so that this error is minimized. In fact, not error is minimized, mean square error is minimized. That is, expectation of mod en square is minimum. We find that solution. So that is the solution of final filter. Okay. So what it does basically, so when you find the filter coefficients using that, you get some equations which we call it the Wiener-Hoff equations. Okay. But the actual concept here is that you have some input and you have a desired response. Okay. And this filter will now generate a output which will be basically very close approximate of this desired response. Okay. By minimizing the mean square error between these two. Not error, the mean square error. So we say this filter is optimum in the mean square sense. Okay. So for this, I don't know whether you are aware about this E operator or this random noise or the random process. If you are aware about this, then you must understand what is the meaning of this expectation, which is called as the mean value. Okay. And then see, when we use this binary filter to find the solution or to find the filter coefficients, we have to make use of two matrices. One is R and one is P, which is called as the autocorrelation and the cross correlation matrix, and the solution is given by W optimum is equal to R inverse P. Okay. So R is the autocorrelation matrix of the input signal, and P is the cross correlation matrix between input and the desired response. Okay. So if you compute these two matrices, you can solve these equations to get the solution where it will lie. Okay. So mean square error, in fact, if you plot it as it is a function of filter coefficients. Okay. So this Wiener filter, it basically finds the minimum mean square error. Okay. So bottom of that surface, if you have two filter coefficients, suppose if you have two filter coefficients W0 and W1, the Wiener filter, it is a two filter coefficients. So you have some input and desired response, and you have to minimize this error. So if you plot this mean square error as a function of filter coefficients, it will be a two-dimensional surface with a minima bowel shape. Okay, so this is the point where the mean square error is minimum. So this is what is given by this Wiener filter. It will give those values of W0 and W1 where the error is minimum by solution of these equations. Okay, and then sometimes if the knowledge about these matrices R and P is not known to you, so you can use adaptive filters. Okay, so adaptive filter is very similar to the Wiener filter. So in that we reach at this Wiener solution using a recursive feedback approach. Okay, now in case of adaptive filter, the filter coefficients, they are not fixed. Okay, they are variable. So what it does, you have a desired response and the output, they are subtracted together to compute error signal, and this error signal is feedback to an adaptive algorithm now here, which is basically used to update these filter weights constantly. This is the structure of an adaptive filter. Okay, so you apply some input and you have some desired response, and you compute the error at any point of time n, and that error is feedback to this adaptive algorithm which is used to update the filter coefficients. It means if you start from time n is equal to 0, suppose you don't know what are the optimum weights where the mean square error will be minimum. So you start from any value. Suppose you have two filter coefficients, you set W0 and W1 this factor to factor of zeros. And then at n is equal to 1, you compute some error, and based on that error, there is some algorithm here which will change these weights. So W0 and W1 weights, they will change from their original value 0 to something else depending upon this algorithm. Okay. So at n is equal to 2, again at next iteration and so on. So after many iterations, and the mean square error will become minimum, this algorithm will stop here. Okay, it means finally it will reach at the one error solution basically. Okay, but it tracks this in a adaptive manner, in a recursive manner. Okay, so this filter is generally used for cancellation of noise when you have this with the signal and the noise they overlap. Okay, we also use this structure for removal of 50 Hz interference and also for cancellation of maternal ECG from abdominal ECG to get your fetal ECG. Okay, so we may come to this again at a later stage. But this is how adaptive filters. So one very example, basic example of adaptive filter that I will give you. Like it is used in this channel equalization, adaptive equalization. What it does basically, it creates inverse model. So you have some input, you give it to a channel, and then you have a adaptive filter here. Okay, yn, and then you have a desired response here, dn. So you have some error signal en, feedback to this adaptive algorithm, update the filter weights. Okay, so if you apply some input to this channel and this dn, which is input or desired response, this is basically same as the input to the channel. So during training phase, the input to the channel and the desired response, they are exactly same. Okay, it means basically your transmitter knows, your receiver knows what the transmitter is actually transmitting. So during that phase only your adaptation is done. Now say this input is given to the channel and the output of channel is given to the adaptive filter. Okay, and the output of adaptive filter, which is yn, which is used to compute this error from the reference signal dn minus yn, and it will adjust the filter weights to minimize this mean square error. Okay, so in the best condition, if the mean square error becomes minimum or it becomes 0, it means the output of this adaptive filter and the desired response, they are exactly same. Okay, and since yn is same as dn is same as xn, it means yn is equal to xn. Okay, so what it actually means that this adaptive filter has created a model which is the inverse of this channel. Okay, so that the effect of channel is neutralized. So if it has a response, you can say h of z, it will have a response 1 upon h of z. Okay, so that when the two systems are in cascade, it becomes a identity system, something like this. Okay, similarly when we use adaptive filters for noise cancellation, what we do, we generally have two sensors for noise. The input to this filter is noise only, and then you have a desired response dn, which is signal plus noise. Okay, and then you compute this error and feed back this to adaptive algorithm, which is generally a least mean square algorithm, LMS algorithm, and update this weights. Okay, now okay, you can say that okay, if it is signal plus noise and it is noise, okay, you can subtract this noise from signal plus noise, you will get signal. No, you cannot say like this because the noise is random in nature, so you cannot subtract it like this. You will have serious signal noise ratio problems. Okay, so what this filter basically now is done, so you have one sensor which captures your signal plus noise. Okay, like we use it in jets for communication between the pilot and the air traffic control on the ground, or for communication between pilots, okay, in the space. What happens in that case, when the pilot says something, speech of the pilot, it gets mixed with this noise in the cockpit or this engine noise. Okay, so you have to remove this engine noise from the speech of the pilot. Okay, so we have one sensor now which captures this desired response, which is signal plus noise. So it may be a mic which is placed close to the mouth of this pilot. Another sensor we place which captures only noise, or it captures the minimum part of the signal. Okay, so it is a sensor which is placed far away so that the signal part is not captured. Now this noise and this noise, they are somehow correlated. So when you apply this noise to this adaptive filter and it change its filter rates, anyhow it generates the output yn, which is basically a very good estimate of the noise which is present in this signal, so that when they subtract it, it gets minimized. This is how it is done. Okay. Similarly, in the fetal ECG, what you do, now you have one sensor placed on the abdomen which captures your signal plus noise. That is, signal is now in this case my fetal ECG, and noise is your mother ECG. Okay, and we place one more sensor which captures only the noise. That is, it will capture only the maternal ECG from the chest leads. So this I will give input as, this will be now DN, the desired response, and this will be now your input to this adaptive filter. Okay, so when this adaptive filter will operate, it will produce basically a, you can say, estimate of this noise which is present in the signal from this input noise. Okay, this is how it is done. So this is how adaptive filters. In fact, adaptive filters, it is a very vast theory, but the general structure how adaptive filters are used for noise cancellation. Okay, so we generally use where the signal and the noise, the spectrum, they overlap. So in that case, we use adaptive filters. Okay.